Welcome back. This is the remaining part of the chapter named Thermodynamics according to the reduced syllabus due to COVID-19 situation. So in this part of our video, we will be learning thermodynamics of isothermal process, thermodynamics of isobaric process, thermodynamics of isochoric process, thermodynamics of adiabatic process. So we'll start with the thermodynamics of isothermal process. So the word isothermal itself states that the temperature of the system remains constant. So a process in which the change in pressure and volume takes place at constant temperature is called isothermal process. So for such process, the change in temperature delta T must be equal to 0. And this is only possible when a system is in good thermal contact with its environment or surrounding, and there is a transfer of heat from the system to the surrounding. And the most important thing regarding the isothermal process is that this process occurs at a very slow rate. For example, a melting of ice which takes place at constant temperature is an isothermal process. So let us calculate the work done in an isothermal process. When we say isothermal process, we take into account the Boyle's law for ideal gases. Boyle's law states that pressure is inversely proportional to volume at constant temperature. That is, mathematically, the equation of state for an isothermal change is given by PV is equal to constant. If we assume PI/VI to be the initial pressure and initial volume, and PF/VF be the final pressure and final volume of the system, then for an isothermal change, PI/VI must be equal to PF/VF, which must be equal to some constant. So let us imagine an isothermal expansion of an ideal gas. Let the gas be filled in a cylinder and let the initial volume of the gas be VI. And after some time, it attains VF when the gas expands isothermally. The work done in an infinitesimal small isothermal expansion is given by dW is equal to P times dV. So the total work done in bringing out the expansion from the initial volume Vi to the final volume Vf is given by W is equal to integral within the limits Vi to Vf P dV. We know that for ideal gas, PV is equal to nRT. So substituting the value of P equals nRT upon V in the previous equation for work done, we get W is equal to nRT, integration running from Vi to Vf dV upon V. The integration of dV upon V is log of V. So substituting the upper limit first and then the lower limit, the equation becomes W is equal to nRT in the bracket log of Vf minus log of Vi. But we know that log A minus log B is equal to log of A by B. We can write down the above equation as W is equal to nRT log of Vf minus Vi. For an ideal gas, its internal energy depends on temperature. Therefore, during the isothermal process, the internal energy of the ideal gas remains constant. That is, there is no change in the internal energy. So we can write delta U is equal to 0 at constant temperature. Substituting delta U is equal to 0 in the first law of thermodynamics, Q equals delta U plus W. As delta U is equal to 0, Q becomes equal to W. Therefore, Q is equal to W, which is equal to nRT log of Vf upon Vi. The graph shows the change in pressure with change in volume at constant temperature, known as the graph of isotherm. So in a nutshell, for an isothermal process, the equation of state is PV is equal to constant. Then change in temperature delta T is equal to 0. That is a constant temperature process. Perfect thermal equilibrium with the environment. Then the next point to be remembered is delta U is equal to 0. That is no change in internal energy. Energy is exchanged with the environment. Then the total heat supplied is equal to work done. So energy exchange is used to do work. Then W is equal to P times delta V. An isothermal change is a very slow change. The system exchanges heat with its environment and is in thermal equilibrium with it throughout the change. One has to remember that neither of the quantities like Q and W are zero. For isothermal change, total amount of heat of the system does not remain constant. The next concept is the thermodynamics of isobaric process. The isobaric process is that process at which the pressure remains constant. The best example can be quoted as boiling water or making of a soup at constant pressure, normally atmospheric pressure, which is almost constant. If you observe the graphs which are provided by the Department of Meteorology, you will find there are certain curves shown. They indicate the locations having the same pressure in a region. For an isobaric process, none of the quantities delta U, Q, that is the heat supplied, and W, that is the work done, is 0. The graph below shows the work done under isobaric condition. We can see there is an expansion of gas from the initial volume Vi to the final volume Vf under constant pressure. Now let us study the thermodynamics of isobaric process. Isobaric process is that process for which the pressure remains constant. That is, the change in pressure delta P is equal to 0. So we will consider an ideal gas which is undergoing a volume expansion at constant pressure. The initial state of the gas will have a volume Vi and temperature Ti, and the final state of the gas will have a volume Vf and temperature Tf. The work done in expansion is given by W is equal to P times dV, where dV will indicate the change in volume. Therefore, W is equal to P times change in volume Vf minus Vi. Using the ideal gas equation, the work done W can be written as Nr times the change in temperature Tf minus Ti. Also, the change in internal energy of the system is given by delta U is equal to number of moles times the specific heat at constant volume times the change in temperature. So this can be written as N times Cv times the change in temperature Tf minus Ti, where Cv is the specific heat at constant volume and that change in temperature delta T is equal to Tf minus Ti is the change in its temperature during isobaric. Therefore, according to the first law of thermodynamics, the heat exchange is given by Q is equal to delta U plus W. So using the above two equations, we can write Q is equal to N times Cv in the bracket Tf minus Ti plus Nr Tf minus Ti. As Tf minus Ti appears to be common, we can write Q is equal to, in the first bracket, NCV plus Nr times Tf minus Ti. Taking N outside the bracket, we can write Q is equal to Cv plus R times Tf minus Ti, and we know that Cv plus R is equal to Cp, that is the specific heat at constant pressure. Therefore, Q can be written as Q is equal to NCp Tf minus Ti. The below graph shows the work done in expanding the gas at constant pressure. The above equation, Q is equal to N times Cp Tf minus Ti, shows that the temperature of the system changes in an isobaric process. Therefore, its internal energy also changes. The heat exchange is partly used for increasing the temperature and partly to do work. The change in temperature of the system depends on the specific heat at constant pressure. In a nutshell, for an isobaric process, the change in pressure is equal to 0. that is, it is a constant pressure process, then change in temperature is not equal to 0. Then Q is equal to delta U plus W, that is, a heat is exchanged is used to do work and also to change its internal energy. And W is equal to P delta V, that is, volume changes when. Next is isochoric process. A process in which the volume of the system remains constant is called a isochoric process. In an isochoric process, the system do no work on its environment during this isochoric change. All the energy supplied in the form of heat causes an increase in internal energy. That is, delta U is equal to Q. So, for an isochoric process, there is no change in volume, so delta V is equal to 0. So W, that is the work done, which is equal to PdV, is also equal to 0 as there is no change in the volume. So the entire heat supplied, that is the heat energy supplied, is used to change the internal energy of the system. Therefore, from the first law of thermodynamics for isochoric process, substituting W to be equal to 0, heat supplied Q is equal to change in internal energy delta U. But we know that the change in internal energy delta U is number of moles times the specific heat at constant volume times the change in temperature. Therefore, delta U is equal to N Cv delta T. Substituting this value in the first law of thermodynamics, we get Q is equal to N Cv times delta T. The graph shows here the change in pressure at constant volume. Therefore, in a nutshell, one has to remember for isochoric process, delta V is equal to 0. No work is done because the volume remains constant. Heat supplied is used to change the internal energy and the temperature of the system changes. Now we will concentrate on adiabatic process. It is a process during which there is no transfer of heat from or to the system. For adiabatic process, Q is equal to 0 as there is no exchange of heat energy. Heat transferred to or from the system is prevented by perfectly insulating the system from the environment or by carrying out the process very rapidly so that there is no time for any exchange of heat. For an adiabatic process, the change in internal energy is always equal to work done, but a negative work done. The internal energy of the system increases in an adiabatic process. So, for the adiabatic process, PV raised to gamma is constant, where gamma is the ratio of specific heat at constant pressure to the specific heat at constant volume. This value of gamma, that is Cp upon Cv, is also known as the adiabatic ratio. For a process to be adiabatic, there is no exchange of heat energy between the system and the surrounding. Therefore, for an adiabatic system, it has to be thermally isolated from the external surrounding. So, whenever a system undergoes adiabatic change, the temperature and internal energy both changes. We know that the change in the internal energy delta U is given by Cv times delta T. For the work done, W, which is the integral of Vi to Vf, P times dV. Therefore, substituting the value of pressure equal to C upon V raised to gamma in the above equation, we get work done W is equal to C integration running within the limits Vi to Vf dV divided by V raised to gamma. Solving the integral, we get W is equal to C into, in the bracket, V raised to minus gamma plus 1 divided by 1 minus gamma within the limits Vi to Vf, because the volume changes from Vi to Vf. Therefore, W is equal to C divided by 1 minus gamma into, in the bracket, it will be 1 upon Vf raised to gamma minus 1 minus 1 upon Vi raised to gamma minus 1. But we know that for adiabatic change, PV raised to gamma is constant. Therefore, we can write Pi Vi raised to gamma is equal to Pf Vf raised to gamma, which is equal to constant. Substituting this value of constant in the above equation, we get W is equal to 1 upon 1 minus gamma into Pf Vf raised to gamma divided by Vf raised to gamma minus 1 minus Pi Vi raised to gamma divided by Vi raised to gamma minus 1. So observe the factor Vf raised to gamma upon Vf raised to gamma minus 1 or Vi raised to gamma upon Vi raised to gamma minus 1. We can use here the laws of indices. As the base are same, add up the indices. Doing that arithmetic, we get W is equal to 1 upon 1 minus gamma into Pf Vf minus Pi Vi. Therefore, work done W is equal to Nr Ti minus Tf upon 1 minus gamma, which is same as Pf Vf minus Pi Vi divided by 1 minus gamma. Therefore, for adiabatic process, in a nutshell, we can say the equation of state becomes Pv raised to gamma is constant. The heat exchange between the system and surrounding does not take place, so Q is equal to 0 and the system is perfectly insulated from the surrounding, or the change is very rapid. Then change in internal energy is equal to minus W, that is all the work is utilized to change the internal energy of the system. Change in temperature delta T is never equal to 0. So the temperature of the system do changes. The adiabatic expansion causes cooling and the adiabatic compression causes heating of the system. The work done in adiabatic process in terms of the temperature can be written as W is equal to Nr Ti minus Tf upon 1 minus gamma, which is equal to Pf Vf minus Pi Vi upon 1 minus gamma. Remember, this value of gamma can be substituted as a ratio of Cp by Cv by taking into consideration whether the gas is monoatomic, diatomic, polyatomic, etc. Most of the times, an adiabatic change is a sudden change. During a sudden change, the system does not find any time to exchange heat with its environment. Now we will learn the thermodynamics behind cyclic process. What is a cyclic process? The thermodynamic process that returns a system to its initial state is called as a cyclic process. So whenever we take into consideration a cyclic process, the initial and the final states of the system are same, though the path may not be same. So in this process, the total change in the internal energy is always equal to 0. Therefore, from the first law of thermodynamics, del Q is equal to delta U plus W, as delta U is equal to 0. Heat supplied is always equal to work done.